So good morning, this is the second part of the first session. So remember that we saw the Deutsch-Jotza algorithm, and today we will see the Simmons algorithm. So first we will see the problem, then we will see the circuit, and so on, okay? So there is a bit, Simmons algorithm is a bit more, it's not complicated, it's quite straightforward too. But there is a classical post-processing that is required, and that's what makes it interesting. And so let's see the problem. The problem is that we are given a function, also in black box form, but today's function, it's not an n to 1, the size of the bit string, the input and the output, it's not different. Now they have the same size. So we are mapping the space of strings of zeros and ones to the same space. In Simmons' problem, this function can be one of two kinds. It can be one-to-one, which means that for every f of x and f of y, it's different whenever x and y are different. So it's one-to-one means that all of the inputs and all of the outputs are considered, and for any two different inputs, the output is different. Okay? This is one of the possibilities. And the other possibility is that it is 2-to-1 with the following structure. Okay, so the first possibility is that f is one-to-one. That means for any two different inputs, we get two different outputs. And the second possibility is that it is 2-to-1. That is, only half of the outputs are considered because the inputs go in pairs to the same value. Okay, so in the case 0, 0, 0, 1, 1, 0, 1, 1, a one-to-one function, for example, would map each of these four possibilities to these four possibilities, okay? So, for example, this to this, this to this, this to that, and so on. Okay, so each of them to a different possibility in the one-to-one example.
And what do you mean that f of x is different of f of y and x?
No, this means f of x is different to f of y wherever x and y are different. No? This, if x and y are different, f of x is different to f of y. If you want, reverse the order, but that was the idea. So that, and in the second case, what we get is that the values, the inputs go in pairs to the same value. For example, this to this one, and this to this one, for example. Okay, so the values go in pairs to the same output. This is what it means to be 2-to-1. And in this second scenario, the values that converge to the same value must be related with this equation. Okay, this is the bitwise addition, which is an XOR of each of the values. And in this case, this is the relation that both inputs must obey. And in this case, this constant S can be seen to be the 0-1 bit string. So 0 and the 0-1 converge to the same value because they satisfy this relation. And the 1-0 and the 1-1 converge to the same value because they satisfy also this relation. You make 1-0 plus 0-1. The 1 with the 0, you get 1, and the 0 with the 1, you get a 1 again. So you get the other value.
Okay, and in the case of the 1-1?
The 1-1 XOR 0, 1, 1 with 1 makes a 0, 0 with 1 makes a 1. You get this other thing. Yep. From here you go to this one, and from this one you go to the other one. See, yes, this relation in the bitwise product, it's satisfied. It doesn't matter if you make it in one of the others or in the other one. This is why it is ensured that if this is satisfied only for values that satisfy this relation, it will be 2 to 1. For x and y, you get a single final value.
Yes.
Hang on a second. Giancarlo had a question before.
Yes, the objective is to distinguish those two scenarios, or?
Yes, the objective will be to distinguish between these two scenarios and to estimate the S and to guess this S value. That will be the objective. Yes, Carlos?
The S is common throughout all the cases.
S is common to for a fixed F. There is one S.
For a fixed F.
Yes, for a given F, there is only one S which satisfies this.
But F, you mean
A function that is not arbitrary. Okay. You remember that in those Jot algorithm we required that F was either balanced or constant, no? Because here we require F to be either 1 to 1 or 2 to 1 with this structure, because this structure is not general. Okay, you could find a function not satisfying one of these conditions, but here we restrict our space of Boolean functions to these ones. Yes, it's important to have these ideas clear in order to understand the algorithm. So,
Quick thing, when you say fx equals the different to y, you mean if and only if x different to y, right? Okay.
okay.
I think one means this arrow should go from right to left.
Which one?
This one-to-one definition.
Yes.
If x does not equal y, that implies that f of x is not equal to f of y.
Yes, that's true. And we also have the other way relationship, because the input and the output spaces are equal. And that's why you have this if and only if. Yes.
Can you give an example for which the 2 to 1 does not exist on S? I mean, you have to go to 3 bits.
I think we have to go to 3-bit to see an example of that. Maybe, yes, because in any pair that you find in only 4 strings, you can find an S. But if you add another one, it's easy to find an example. For example, imagine a function that maps the 0, 0, 0 to one value, to 0, 0, 0, 0, 0, 1 to the same one, and now we map, because I want, the 1, 1, 0 to 0, 0, 1, and now in order to satisfy this property, the other value mapping to 0, 0, 1 should be 1, 1, 1. Okay? By now, if I choose, because I'm defining an arbitrary function, that I use this other string and map it to the 0, 0, 1 value, and then define everything so that it is 2 to 1 but not satisfying this relation, the S that you get from here is 0, 0, 1, but the S that you get from these two is 0, 1, 1. That's it. So they are different. And we are not considering this case. In our case, what we should have is that 1, 1 is mapped to this one, and that's why you get this.
Okay, I don't understand. So say that it only has two scenarios. It is
That's
either
it.
1-to-1 or it's 2-to-1, but with the restriction that things that equal the same
And,
are
yes.
distanced mod 2, have some distance mod 2, called S.
Yes.
Okay. And then
Yes.
the sum mod 2 of a bit string is the sum mod 2 of each one of the bits.
The sum of
The sum mod 2 of the bit
mod
string
2.
is the sum mod 2 of each one of the bits. Because we're doing
Yes, in this case, yes, but be careful with the arithmetic sum, because in the arithmetic sum usually you have to carry the value. For example, if you sum, if these two are numbers represented in binary representation, and you are adding them, you have to carry the value, because it's 1, 1, 0. You carry 1, 1, 1, 0 again. You carry 1.
And here you carry nothing.
And here you carry nothing. What we are doing here is the XOR, that is the bitwise bit flip. 1, 1 goes to 0, and then 1, 0. These two are different.
Great.
And what was the name of this operation?
I don't really know, but I think this is the arithmetic sum, modulo 2, and this is either the XOR or bit flip, or maybe it's also a sum, bitwise sum, something like that. I don't know, but usually these things, when you are working with bit strings and you are using them as bit strings and not as numbers or something, it's used in this thing. It's used also this other thing. So it is a bit of a mess sometimes, but yes, in this case we are considering this. Okay, so this is the problem that we have. We have a function which can be either 2-to-1 or 1-to-1, and if it is 2-to-1, there exists an S that defines the relationship between the two input values that go to the same output value. Okay, and now we will briefly see the circuit first, and then see what the action of this circuit is in our initial state. Okay, so we have two registers. One we will use for the input, and other one we will use for the output. Okay, both of them have n qubits. In the Deutsch algorithm, we had a similar structure where we have n inputs and only one output qubit, because our output was only 0 or 1. But here we need to represent n. So similarly, we also apply a Hadamard gate to obtain a superposition of all of the values, but today we won't apply any Hadamard gate in the lower registers. We will leave it like that. Afterwards, we apply the oracle that we met the other day. So here we have the input, here you have a second input, and here you store the output. Remember this guy? We all remember this guy. This is a... Okay, we will see what form the state takes here. Okay. And then we have to reverse the Hadamard transform. And we do nothing here, and then we finally measure both registers. So in the Deutsch algorithm, we only need to measure the upper register, but here we'll measure both and use the information on both of them to solve our problem. Okay. So let's name each of the steps. This will be 1, 2, 3, 4, and the state of the measurement, okay? Okay. So let's start. So the initial state is pretty simple. 0, 0, 0 state. Then the second state is the state after a Hadamard transform of the first register. This sum is over all of the possible bit strings. Okay, I'm not writing it down because it's a mess instead, but for you to know. X. Is it too small or is it okay? Yes. Yes, I can. The problem is that if I make it bigger, it's like super ugly for me. But, okay. Okay, so I remember the X is added for every possible bit string. And now here I represent this with a tensor n in order to represent that it is to all of the register, but here as X already stands for the whole bit string, I don't write that n, tensor n, in case. Okay, now we calculate the function with the oracle, so this is this step. And we get an entanglement between the first and the second register, between the input value and its corresponding output. All right, so now we have all of the information that we need here, but we want to extract this. And we will do a similar transformation to the previous days. Set. Also for all of the input registers. Remember, this is the bitwise product between X and Z. Z1, S1, Z1 plus blah, 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 Xn, Zn. Well, I guess I wrote this in this other way the previous day with the bitwise with XOR, but it doesn't matter because it is in the power of a -1. Okay, so in the previous day,
Sorry, when you do this bitwise product, then you do all the products, then you sum the results. But this arithmetic sum or
that's what I was saying. Yes, it is technically. I think it is the XOR sum, the XOR sum, but it could be an arithmetic sum because here it only matters the parity of the results of the result. But yes. Okay, so in the previous day here we have also a term that added the value of the function or something like that because that's what because we constructed a particular input state for it, but today no. Today we only have this structure. And now we have to measure both of the registers. I'll have to see what values we can obtain. So up to here, everything is okay? Yes. So let's see what we can measure. So the probability of a state set will be the norm of this state. All x minus 1, x times set. So I have done almost nothing here. This is like the trivial part. And now we, of course, I didn't tell this, but in this case, we are considering S which are different to the 0 string. Because if not, you are in the previous case, and that's not 2 to 1, strictly speaking, okay? So, just in case. Yes?
f of x in the measurement, you are just
here we are measuring here only the first register. Yes.
the trace.
Yes, I guess more or less. Well, this is the amplitude of the state set. Well, the amplitude, the probability to measure the state set. But yes. Yes, we'll focus first in the set, and then we, of course, if you obtain a particular set, you will obtain. No, that's nothing to do. Okay, so maybe this measurement is not required actually, but maybe. Yes.
I'm slightly confused as to why the minus 1 would have an exponent of x times z and not x plus z. I'm not sure where the product came from.
Yes, it comes from the Hadamard transform of an arbitrary state. And this comes because, if x is either 1 or 0, okay, so if you are in a single dimension, it's easy to see that what you get is minus 1 x times 0, 0 plus minus 1 x times 1, 1, which is 0 plus minus 1 x. That is, if x is 0, you get the sum of both of them. If x is 1, you get a minus in the second one, which is what you expect from the Hadamard transform. So if you combine this structure for a bit string of x's, you get a product here up in the exponent part. So that's what you get when you get a bitwise product, because it's the addition of each of these terms here. Yes, so that's why it appears here. Try to do it if you want, because it's once you see how it works, it's easy to see. Okay, so now we can separate the two possibilities that we had. Either f is 1 to 1 or it is 2 to 1 with that structure. Yes?
Yes.
I will erase the first steps, yes, okay, to have space for this second part, okay? Okay. Can I erase this, Giancarlo? Yes, no? Sí.
Yes.
Uh-huh.
In the case that you are in a superposition, then you have to apply the effect of the Hadamard independently in each part, or how do you do it?
You mean, repeat your question, please.
So,
if you're on a superposition, you apply, yes, you in order to know how to apply the Hadamard, the easiest way is to represent your state in the computational basis and to apply the Hadamard to each of the states of the computational basis. So if you, in the single qubit case, yes, yeah, and that's what we were doing with the sum in the previous case. Okay, so now let's see what happens if the function is 1 to 1. If it is 1 to 1, then if it is 1 to 1, qué majo soy, no me he puesto el proceso. If it is 1 to 1, then every f is different, okay? So as every f is different, this as every f is different, we can add up the amplitude of each of the f's. Because as every f is different, it's like if you have, here, if you want the norm of this vector, as each of these vectors is different and they form an orthonormal basis, you can, this is only the sum of the amplitudes. Yes, so the same happens here. If every f of x is different and you have all of the output state there, then the norm of this vector will be the sum of the amplitude of each of the components, because they form an orthonormal basis also. So it's this very same thing. And as this, the modulus of this number will always be 1, and it is added 2 to the n times, because there are 2 to the n different possibilities, what you get finally is 1 over 2 to the n, which is independent of the set that you are trying to measure. Okay? So if we get, here we won't obtain the result with a single measurement, we will have to perform many. And if we get this output distribution, we will know that we are in that case. But it won't be easy, we will see now. But that's just an idea. And then in the 2 to 1 case, now these, there are at least 2 values that obtain the same f of x. So we cannot do this thing, because there will be 2 values that will have the same f of x, and their amplitudes should be added with a phase, not only their absolute value. So take, okay. So we will get y from the image space. So y is a possible output of f of x. And remember that this image space has half of the dimensions of the original one. There are half of the elements. Because for it to be 2 to 1, you must have less output elements, okay? And we will define x1 and x2 as the input elements that output that y value. And we know that they satisfy this property for some s. Yes? Okay. Then we can rewrite this sum as a sum over the outputs, y, considering each of the possible phases. So we have -1 x1 times set, yes, plus -1 x2 times set. Here we have y. So we have substituted the f of x with a variable, and now x of x1 and x2 depend of y, okay? Because they are the values that satisfy this. Now we use this property, and now we can again use the property that we have used above, because the y's are orthogonal between them. Then we can again simplify this thing. Okay? So this is the very same property that we use here, that as each of these states are orthogonal between them, we can, in order to consider its norm, we can add the square of the absolute value for each of the amplitudes of each of the states. And here it comes magic. And is that as x1 and x2 satisfy this relation, we can take out the x1 set. Yes. Okay, so this is not so trivial, but we will see. What we originally had is that x1 times z minus 1 x2 z. And here we substitute this thing in here. No. And due to the properties, because if this is, yeah, okay, so this can be done. Yes. Okay, so here, this is what we originally have here. Then we substitute in this x2 times bitwise product with z. We substitute this relation, this. Then we must convince ourselves that this is true at the product, the sum of the exponents is the product of this. Yes, because the thing here is that it only matters if this is even or odd. So the relationship, this holds, okay? And now we can take this thing as a common factor to the previous one. Yes? Okay, so now that we have this, and this is important. Now that we have this phase doesn't affect the final result. Okay. And here again we have two different options. Either z times s times z is equal to 0, and in this case, if we add all of the values as this is half of the size of the space, you get times 2 to the n half. And if s times z is equal to 1, so in this case we have all of these terms, maybe times 2. A ver, 2. I'm not doing it okay. Yes. This is 2 over 2 to the n. So this one with this one, and one of these ones goes with one of these ones, and you get 2 over 2 to the n. Okay, for every set satisfying this relation with S. And if S times Z is equal to 1, then the amplitude, the probability to measure that state is 0. patatero. Yes. So here we have arrived to this equation for any probability to measure set, and we have two possibilities: either s times set is equal to 0, and in this case you have a fixed probability, a constant probability. Either it is s times set is equal to 1, and then you have a 0 probability. What was this for? Yes, okay. So if s times set is equal to 0, this term is a 2. Okay? So we have 2 squared added 2 to the n times over 2 because we have only half of the space, and then we divide it. So thank you for asking. Okay. Yes? Why is it evenly distributed? Because we have, because of this, mainly because of this property. As you can write the inputs. Yes. Yes. I am not understanding the question. Sorry, please.
You have assumed that for the half-ball sets, you have S times set is 0.
S times set is either 0 or 1 because it is the bitwise product, and the result of the bitwise product is either 0 or 1. So we have two possibilities. If we are in the first scenario, we get this, and if we are in the second scenario, we get this other part. In the first scenario, we have found that it doesn't matter the particular value of set because you will always have this thing for every y.
This is the modulo 2 of the product.
Modulo 2 of the product. Okay, yes, also. Okay, so now we have two possibilities. I will erase all of this. So here what we have is that either if s times set is equals to 0, we have this probability to measure it. If s times set is equals to 1, you won't measure this. And here you get 1 over, yes, for any value, for any set. Okay? So we might realize here that if we consider this a case where s is the case where s is 0, if we now consider that this is a s equals to 0 case, you may realize that here for every set you also get s set times s equals to 0. Okay? So what's the nice thing here? That either if you are in the 1-to-1 case or in the 2-to-1 case, you can only measure s times set equals to 0 cases. Okay? So imagine that you measure k different values for set. Okay, so we get 1, well, maybe in the upper part to differentiate from the bitwise thing. You get k different outputs. Now you know that for every of these outputs, their product with s will be 0. So you can build a system of equations with this form: 1 times s1 plus 2 1 n n is equals to 0. Okay, 1 and k s n is equals to 0. Okay? You can get this system for the values for the s. So the s1, sn are your unknown values, are your unknown variables, binary variables, and the set1, setn are your known values.
There is
Mhm.
It's 2 to the n. You have a lot of n's, so you are go to 0, and in the limit you are not going to be able to distinguish between anything, no? Because if the probability 1 to 1 goes to 0, the 2 to 1 goes to 0, and the other one goes to 0.
Okay, yes. Yes, again, as in the previous case, we don't really care about the particular distribution of these values. Well, it's important for the mathematical properties, but we don't matter if the probability to measure a particular value of set goes to 0, because we only want to measure sets, a k with k elements that satisfy these equations. So I don't mind whether this is a particular value or another. I only want to get a system of equations to solve this for n, for s of n, for s, okay? So in order to solve this system of the system of equations, we need to have a sample of n minus 1 values. Okay, it needs to be n minus 1 for different sets. Yes, Carlos?
I don't understand what do you mean with S1, blah, 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 S to the Sn.
Okay.
You're measuring one function. I guess every set is one realization, right? And
Yes, it's the output of one of the measurements.
It's constant, right?
Yes.
You always have the same set.
Yes, yes. The lower index stands for the index of the bit string, and the upper index stands for the measurement.
So this is set times S equals 0 extended.
Yes, yes, yes. This is set 1 times S. Okay, okay. I have written this in this manner because the equation, the linear equation, is clear in this way. Okay. Okay. So we will have n minus 1 cases, then this system will yield a solution, S prime. Okay, just a quick note. We are measuring here k different values. We expect them to be different, but in fact, this could be, you could obtain many times the same set because you are unlucky, for example, and you will have to realize more than n minus 1 measurements, okay? You may need more than n minus 1 measurements, but you need at least n minus 1 different values of the output. Okay, that's what we are looking for. So now you obtain a particular S prime as the solution to this system, and now we have to check whether this S prime different from 0, because 0, of course, always satisfies this equation, the 0 string. So you will get an S prime different from 0. And now you have to check whether f of 0, 0 to the n, because it's the 0 string, it's equal to f of S prime. This S prime is the estimation that you have obtained, okay? So now, if these two are the same, this means that you are in the second scenario, that is the function is 2 to 1, and you have found a S different from 0 that satisfies this relation. If you are in this case, okay? Now, if you obtain this is different from 0, this means, this means that actually the S prime that you have found is not a real X prime, okay? Because what you really had was that S prime was equal to 0, and you were in the 1-to-1 case, okay? So if you were in the 2-to-1 case, you arrive to this equation and you solve it, obtaining an S prime, that will be your solution. But if you are in the 1-to-1 case, this thing is only useful, or you are only using it to discard the 2-to-1 case. But it's the most efficient way to do it. Because in the other case, you will have to measure a lot of times in order to see whether you are here or here. But that makes no sense, because if you do this step and you find that this S prime that you have solved for this does not satisfy, that means that there is not S prime that will satisfy it for every string that you can measure, and you are in the one-to-one case. Yes? Any question, please? I don't know what time it is.
How many solutions do you expect to get?
From here, there is only one S prime that solves this equation.
Which is difficult. I mean, there are also the 0, 0, 0, right?
Also the 0, 0, 0. There is only one S prime that satisfies this.
And S prime, in theory, is the S associated with your function.
If you are in the 2-to-1 case, that S prime has to be that S. But if you are in the 1-to-1 case, there is not such an S, and you will obtain a different S prime depending on the values that you have measured, because there is no relation between those values.
Okay, so it will be a curious thing, but not.
Yes. Yes, if you are in the 2-to-1 case, because S is non-zero, this equation tells you some information. But this equation, in this case, tells you no information about S. Well, yes, because there is nothing to say.
How is it, maybe this is super bad.
No.
How is it possible that you obtain some valid S if there is none?
Because if you have n-1 different bit strings for set, and you mathematically you solve this system of equations, you will obtain an output.
But it could be uncompatible, right?
Uncompatible with, if you then measure, if you are in the 2-to-1 case,
Yeah.
then it's another thing. Then you could extend this system of equations, measuring every possible set state, and even if they are more than 1 minus n-1, even if there are more than n-1 different conditions, they will be solvable, because between them they will be linearly dependent, and you will obtain the same S prime.
Yeah.
But if you do this for the 1-to-1 case, there will be no solution, only the 0-0 case.
Yeah, but there couldn't be the case in which even for n-1 you have no solution for the 1-to-1.
I don't think so. I think, yes, because this equation has solution for any set that you pick. If they are different and they are n-1, then there is a solution. I think. Yes.
I am having some trouble with that.
Okay, so the thing here is that this always has a solution with different from 0, but that solution is only meaningful in the 2-to-1 case. In the 1-to-1 case, that solution is a spurious thing that you can use to tell if you are in the 2-to-1 or in the 1-to-1 case. And this would solve the problem.
How do you check that condition?
This?
You have to check with the oracle again.
Yes, you have to check with the oracle again. Yes.
And
Which
which is the
is the? Of the oracle? Of the algorithm. Yes, we are going to that here. Yes, because in order to be fair, we must consider the probability, how many measurements you should take in order to obtain this system, because you could obtain the same set once and again, and that in principle is possible. So we have to check the quantum complexity too. Okay. So in order to obtain each of the measurements here, we have done an oracle call and one oracle call. This one. But we are calling it at least n-1 times. So what's the probability, for example, that we success only measuring n-1 times? So it's the probability that in all of the cases, for each k, from k1 to n-1, is the probability that you measure a string that you have not already measured. And this is more or less 0.284 which is a bit higher than a quarter. So the probability that you measure, that you can solve the problem in a constant number of calls, which is n minus 1, is this one. It's above 25%, which is not bad. And you can, changing this number, you can make arbitrarily high this value. In the limiting case, if you measure all of the possible outputs or you make a lot of measurements, you will obtain almost with certainty the solution to your problem. No.
But I guess that's never one because
Never
you
one.
can
Yes.
repeat the measurement of the same.
You could always be super unlucky, yes. That's true.
You could, isn't it enough to measure half of the inputs?
Yeah, but the thing here is that you are not choosing what output you measure. You measure your quantum state, and you may obtain the same value once and again. And that tells you no information about this. You need to obtain different values in order to obtain information. And you cannot choose what to measure.
But this is you're comparing with a classical strategy.
Not yet.
Okay.
Not yet. So this is in order to see that this algorithm, in order to have a fixed probability limit, this bound scales with n. Okay? I'm not being super mathematically formal.
But there is something I have not clear. Sorry. If you measure n minus 1 things, you don't have less than a quarter to know. You have 100% probability of knowing because then you do the system of equation stuff and then you know. Right?
Okay, sorry. This is the probability that you measure in n minus 1 steps, n minus 1 different states.
Okay.
Yes. So yes, in the generalization of this is to consider the probability to all the different probabilities, to not measure that. Okay, so it's not super easy, but it can be shown that this factor, that you can bound the probability of success with a constant value, in this case 1/4, with performing measurements in the order of n. Okay, so the amount of measurements that you have to take to success with a fixed probability or bounded probability is in the order of n. There are n oracle calls involved, more or less. So you can be more detailed in obtaining which is the actual bound, but this gives you the idea. Okay.
For example, if you have n, you are looking at n system, and you measure all the case, and for example, not 1 or not 2, you have to still look at you measure n minus 1, or you have some resistance that you measure all the case, you get a good result.
Yes. Arithmetically, you cannot solve the system of equation without measuring n minus 1 different values. So you need n minus 1 different values. If not, you could get different s. That's possible, in fact. You could get different s values that satisfy your system, your reduced system of equations, and then you will have to check which of those strings satisfies this relation. Okay. So just to end, the classical algorithm, well, is it okay? Everything okay? Okay, then the classical algorithm, we have also 2 ways to solve it. I don't know if you want me to be detailed or not on this, but there are 2 ways. There is a deterministic way, of course, and a probabilistic way. So in the deterministic limit, you need classical deterministic. Then you need to try, well, this is one of the possible approaches, but it's an idea. You need to try every possible S prime with many inputs, Q, in order to discard that S is equal to 0. Okay? So checking different S primes scales with 2 to the n. And then checking in the worst case scenario half of the possible input values, this will be 2 to the n half plus 1. That is, you have to look for half of the input values plus 1s in the worst case to distinguish between the 1 to 1 and the 2 to 1 case. This could happen. So this scales as 2 to the n minus 1. Okay, so the whole system is 2 to the n, it's exponential in a deterministic way. In practice, what you actually do is more efficient than this, it's a bit more efficient than this, and is that you take a set of x's, 2, 2, 2, 2, which satisfy this equation, this condition. But, that is that you take a set of possible inputs, whichever you want, which satisfy this equation. That is, they span all of the possible bit strings performing the bitwise product. Okay, so this is a particular condition, and if this set satisfies this particular condition, you can solve this system only checking the values of this value of this set. Okay, and in this case, it has been shown that any deterministic algorithm scales with 2 to the n half, which is better than checking all of the values in a like brute force manner. Okay, this is a bit more sophisticated, but still it scales with the exponential 2 to the n. And now, to be fair, we must compare also with the classical probabilistic. So in this case, instead of using a set that satisfies this equation, which of course will be quite large because k will be quite large, it will scale with 2 to the n, you take only a constant, a reduced number of values from that set. Instead of checking to all of them, you take a fixed number, which is here it must depend on 2 to the n, on the to be bounded, and so on, with this set. Okay, and now you try the function for each of them, and you can bound the probability for a given k. It can be shown that k must be in order to have over 4. So this is also 2 to the n half. Okay, so given us a fixed set, you will get a good solution to your problem in some cases. So if k is larger than than this factor, you will get a probability. You have a probability of success of 3 over 4. Okay. So and you could choose another probability, and you would obtain another bound for k. But the thing here is that also in the probabilistic scenario, the complexity is this one. So in both cases, the quantum approach, which grows linearly with n, in the oracle complexity, in the query complexity, it's better. And that's all of the algorithm. So sorry for being late again. Yes?
I have a meta question. How possible useful do you think would it be to explain Simon's algorithm in terms of a basis transformation of the UF? Because I see that many algorithms are something that is classically understandable, surrounded by caveats. So usually these things are explained in terms of, okay, these are input gates, we multiply these gates, we apply this, and now this is our output. Because usually it's easier to explain in terms of gates for someone who is just entering quantum stuff. But we can work with gate graphs, we can work with transformations, so would it be better for us to not lose the physical picture by talking in terms of basis transformations of gates? A basis transformation of UF. Do you think it would be clearer to not lose the physical picture?
I don't think I'm able to solve that meta question or to dissert about that meta question. If you want to give your opinion.
It's kind of an open question. Maybe we could get more insight trying to understand these things as basis transformations. Because it's always two elements surrounding itself.
Maybe. So this is a basis transformation of this state. Yes.
Part of UF.
Okay. Yes, I guess. Maybe. So.
I have one question. Is this thought to be useful, or is also kind of a curiosity like the chat?
I think it's also a bit like an academical example, like the Jyotsas. And this example is important compared to the Jyotsa because the Jyotsa shows an advantage with respect to the deterministic, classical deterministic approach, but not with respect to the classical probabilistic approach. Because in both cases, the asymptotic limit is, the asymptotic complexity is constant. But in this case, Simon's algorithm also shows an advantage with respect to the classical probabilistic approach. Because Simon's algorithm is polynomial and the classical probabilistic one is still exponential on n.
It's like an historical performance, right?
Yes, and also it's important to understand this because the ideas behind this algorithm are also present in other hidden subgroup problems, which are very typical, which are quite important. So this structure of Hadamard, classically function Hadamard, is very typical, and to get familiar with the steps and how to, different ways to interpret and to take advantage of the output, because in the previous algorithm, the output was your measurement directly, and there was almost no classical post-processing, and here you have to solve a linear system of equations, and so on.
Yeah.
And I don't think if the resolution of that linear system of equation is considered, I don't know if it is considered in the query complexity, because technically those are not queries, you only care about the queries, but then you have to solve a system of equations. So to be fair, we will have to know what's the computational complexity of implementing this oracle, of implementing the classical oracle, and also then the post-processing part. But well, still, in terms of query complexity, it's an interesting example. Planning. Okay.
Even in the query complexity, Simon's algorithm is useful only for a certain regime or probability, because at some point the deterministic algorithm is much better in complexity than the quantum.
Yeah, that's true.
So that probability of 3/4 is the limit at which the two probability crosses. So the probability of success with the quantum and the probability of success with the classical.
No, the classical, well, I have not analyzed the actual limit of the probability related with the size of the sample in the quantum limit. I have only give like a hint of where it comes from. And here the same. This is like a hint of where this comes from. So if you are interested in a probability of 3/4, then you use that bound for the k. But if you want a higher probability or a lower probability, you will get another bound. But all of them depend on the square root of 2 to the n. That's the thing. For a constant probability, you get a dependence of the size of the measurement that you have to, of the size of the system that you must consider according to that. Yes.
Interesting problem to see where that probability crosses. So when it is better, so if I want
Yes.
to have a probability of 0.9999,
Yes.
is it better to use the quantum or the classical?
Yes, in terms of query complexity, but that question may only be useful if you have only a measurement of the computational complexity of each of the oracles too, because of course that can be very important.
And in general,
Yes, if you are the query complexity is interesting for the asymptotic limit, but it's not so interesting for a particular application.
yeah,
Because in order to make your question, you must know the answer to the other question, because then this is like an estimate. You are estimating that the cost, the time cost of each of a query in a classical and in a quantum computer is the same. That's not fair.
yeah, no, because obviously classical is much faster.
That's not fair. Then yes, you should consider the time, and you will be able, in principle, to compare the time required by each of the approaches.
Because in this case, the query complexity, the classical query complexity is 1. Because it's just taking one cable to this other cable.
No, yeah, no. It depends. It depends. No, in general, as Javi said the previous day, the query complexity, the complexity of implementing a Boolean function in general is 2 to the n to 2 to the n, so you have a lot of combinations. So it's not 1.
Yeah, but you only need a multiplexer. And the query
Yes, of course, a multiplexer of the size of 2 to the n. Yeah, you don't have that multiplexer. You have to implement it with logical operations too. Well, complex logical operations, but yes, with multiplexers. But yes, that's true. In principle, in a classical computer, you may implement somehow this oracle so that the complexity is 1. But with a quantum computer, maybe that's not that easy. Of course, it depends on the resources that you get. So we have finished. Thank you very much. And see you next time. The next seminar will be in a couple of weeks or so.